Great. Thank you very much, Mila and Jane, and for everyone else who's been associated with the organisation of this. It's a fantastic chance to get together, and it's a real pleasure to be here and to be speaking today. I'm going to talk about some experiments that we've done in collaboration with Mila and co-workers, and my PhD student Farzad will be following up and talking about some more stuff along that way as well. So something a bit more concrete. I think there's only a few experimentalists here, so hopefully I'll keep the level of the talk not too technical, but introduce a few things as we go along. So given that we're sort of looking at forming new collaborations and trying to talk about what capabilities we can bring together, I thought I'd tell you just a little bit about my group and about Centre for Quantum Dynamics at Griffith before I kick off. Here's a photo of people which is particularly relevant because Nora and Farzad, you might recognize them, you might have met them already. They're here at the conference today, this week. So please say hi to them if you've got the chance. Okay, so Griffith University is in Brisbane, Australia, if you haven't heard of us before. And my lab, the Quantum Optics and Information Lab, is in Griffith Centre for Quantum Dynamics. Griffith's in Brisbane. It's a beautiful place, lush forest, not too far from the beach, a nice city. Howard Wiseman, who's here at this conference, is our director. And the centre as a whole performs experimental and theoretical research in a variety of areas around quantum physics, optics, biophysics and things like that. So both experiment and theory, and we have PhD positions available if anyone's interested in coming and joining us, either my group or the other teams. In my lab, we do quantum information research with quantum optics, and so we look at things like quantum computing and metrology. So recently we looked at a 3-qubit Fredkin gate realized with optics, and some small algorithms you could do using swap tests and things like that, published last year. And we've done over the years a variety of things, looking at beating the shot noise limit, using adaptive protocols in particular, a lot of that work done in collaboration with Howard Wiseman. On the technical side of things, we're interested in improving photon sources and detectors for quantum communications experiments. This here is a experimental diagram of an entangled photon source that produces very high purity photons with very high heralding efficiency. So we get a pair. When you detect one with extremely high probability, we can collect and detect its partner. We can make them pure by having factorizable frequency spectra. It's a technical issue, but an important one. And that means that we can get really high visibility non-classical interference between pairs of photons, which is a resource for all sorts of communications and information processing protocols. And then we can use those kinds of sources and the related technology to do things like, target the problem of photon loss in sharing entanglement over long distances, whether that be for communications protocols or other things like this. And so we have this entanglement swapping based protocol, which basically means that we can look at some non-local test, an EPR steering test in this case, which ordinarily we wouldn't be able to violate. The data is below these bounds because there's way too much loss, but by heralding on this entanglement swapping process, we can verify non-locality over losses corresponding to long distances. So without going into too much details, what I'm telling you is that there's a variety of different things that we're able to do, and we're continuing to develop technologies that allow us to do that. So even if we're not talking about complexity science, if you're interested in talking about our capabilities to do other kinds of experiments, please come and have a chat. So our interests in the lab as a whole, fundamental optical quantum information science or fundamental quantum physics perhaps, things like entanglement, quantum measurement, and of course now we've introduced complexity to this list as well. We're interested in doing the science towards technological applications in quantum information science, entanglement sharing for communications, improved processing, and something that's related to quantum complexity, as I'll talk about now, is less memory usage. And of course, even though we're scientists and not engineers, we still have to do a bunch of technological development to keep making new protocols and new ideas possible in the lab. Okay, so let me come back to the topic at hand. Experimental quantum enhanced memory use in modeling stochastic processes. This work is done in the Quantum Optics and Information Lab at Griffith University, and parts of our work are connected with the Australian Research Council Centre for Quantum Computation and Communication Technology. Of course, I should acknowledge our collaborators on this work. On the theory side of things, we've got a very close contact with Mila's group and with Jane and Wei Yip and others, and as I said, Howard, our collaborator at Griffith. And the experimentalists who worked on this, the PhD students Matt Polson and Farzad Junagani, Joseph Ho contributed a little, and Nora's recently joined our project as well. Okay, so I've given you the lab overview, and what I want to talk about in the rest of our time is the idea of complexity and stochastic simulations. So Jim gave us a really interesting and broad outlook with lots of historical perspectives, philosophical questions, an amazing overview. I'm going to drill down to just a couple of the things that he talked about at the end there. Notions of statistical complexity, notions in Farzad's talk, he'll go on to talk about ambiguity of simplicity and things like that. I wanted to look at two particular experiments that we've done. One that I'm calling the random switched model, or the perturbed coin, and I'll introduce you briefly to this 1D Ising model, which Farzad will talk about a little bit more in his talk. And then we'll just highlight maybe a few future directions. So we're interested in stochastic processes, and in particular the information complexity of them. So stochastic processes are important in social and natural phenomena. We can think about all kinds of things that we can model, the stock market, perhaps weather and climate, things like that. Systems that may have some degree of determinism, in fact, but because we can't understand all the details, then we can model them as a stochastic process, possibly as a time series of the kind that Jim spoke about before. So we're interested then as this collection of random variables indexed by time. Okay, and so the probabilistic behavior of each of one of these is governed by this joint probability distribution between the past and the future. Okay, and so the past is this sort of indexed series of random variables here, and the future going from time 1, time 2, off to positive infinity. Okay, and so this joint probability distribution between the past and the future really defines the problem. So we're imagining some sort of system here, and there's all of these past events, past outcomes here, and then we have these future ones on this side, and as time progresses. Okay, and so although what I've drawn here is some sort of model, I'm imagining that this thing stands in for whatever physical system that we're interested in looking at, whether that be the stock market or something else. And so during this talk, I'm going to use the word system. And okay, so I guess one of the things that we'll have in this conference is an opportunity to talk about the terminology we use and making sure we use the same language. But at least for the duration of this talk, I'm going to refer to the physical thing that we're trying to model as the system. All right, so as I mentioned, stochastic processes are often used when there's a perhaps deterministic process which is too complex to model from first principles. And so we've got this notion of some sort of black box that the process is defined by its output. So we take a look at what comes out of this, and what comes out are some statistics, some, in this case, a series of bits, zeros and ones that tell us, or that in some sense define what the process is. Okay, and so if that's the system, what we're interested in doing is modeling it using some other system to model it. And in fact, at the moment, I'm just thinking of an abstract mathematical representation when I use the word model. So what we're looking at is having some sort of mathematical model that's parallel to the system, so that when the system itself evolves from time t1 to t2, the model itself produces output that's consistent with the system. These things, in some sense, are equivalent to one another. That's what we're interested in by modeling our stochastic system. Okay, but of course you can imagine one might have a very large variety of models for any given system. Okay, you could have some model here which has some memory, some internal parameters, and it produces some sort of set of statistical outcome. We could have a different one, in this case with a smaller number of internal parameters, a smaller amount of memory that's required to be stored. And in this case, these two models, Model 1 and Model 2, produce the same statistical outcome. Okay, the statistics of the output is identical. Okay, in this case, the actual outputs are identical, but that need not be the case. And so the question is, well, which of these two models is better? And I think the notion that we probably all have intuitively is that the simpler model, the one that requires less internal parameters, the one that requires less memory to, of the past in order to predict the future, is the better of the two. And Jim introduced us to Newton in the Principia and mentioned Occam's razor in passing. This idea that what's the minimal amount of information that we need about the past in order to predict the future. All right, let me introduce to you now then a very specific case, which is one that we looked at in the lab, which I'm calling the random switch model, but you might know it already as the perturbed coin model. So this this experimental work is about to appear in Science Advances next month, but in the meantime you can read it on the archive. Okay, and this is what our model, this is what our system that we're modeling looks like. We imagine that we have two switches. They're binary switches, so they can be on and off, 0 and 1 if you like, and the system we're imagining at some time Tj. Okay, and so what happens in this system is that as each time step progresses, one of the two switches randomly with some probability p changes its state. Okay, or obviously 1 minus p doesn't change its state. So here we go. We're going to the next time step. Probability p. The system might change. Okay, the first switch here has gone from on to off, and in this particular system, we're imagining that our output is just given by whether the switches are in the same state or in a different state. Okay, which we can get from this XOR operation that will give us the output of this system at time j plus 1, tj plus 1, the output we denote as x j plus 1, and so now we have our system in this state at time tj plus 1, and we can just continue with this over and over. And so we might ask, what kind of model do we need to represent this? And a very naive model would be that we need to store the state of the first switch and we need to store the state of the second switch at all times. But a moment's thought would help you to see that, okay, all we're really outputting here is whether the switches are in the same state or in opposite states, really the parity of the switch, as it were. And so that can be described by a single bit of information, and none of the other information that you could store is really relevant to the problem. And so this problem can really be reduced then to a simpler model, which is just this perturbed coin model, which has two basis states, if you will, a 0 and 1, just one bit of information. And the question is, do we transition between these? Well, that happens with probability p at each step, or we stay in the same state with probability 1 minus p. And this model for this system has this very simple equilibrium state where we spend equal amounts of time on average in state 0 and in state 1. And so these sort of probabilities, lowercase p, of occupations of these two states is a half in the long term. All right, so let me now introduce the idea of epsilon machines, which we heard a little bit about just a moment ago. The models that we're interested in implementing are epsilon machines. So if we have the set of all possible past events, and we have two sets of past events, if you will, that have statistically identical futures, then the information that we need to distinguish the two pasts is really irrelevant if they predict the same thing. We can throw away any information that's not required to simply predict the future. And that will reduce the amount of information that we need to store. In fact, we can make this equivalence diagram, or we can make this diagram where we break up the state of all possible pasts into these equivalence classes, where being in one particular class, S3 let's say, means that you predict the same future. And then really we just need to store whether the past, which one of these classes the past belongs to. And these things are called causal states. and that's what we're interested in storing. And a machine that really has its internal state as these causal states is called an epsilon machine. So the idea, just to summarize, is that there's no need to distinguish between different pasts if their future is the same, and the epsilon machine captures this notion. Okay, so here's a beautiful picture that I borrowed from Miller. The idea then is that this is the representation of the information stored, or the information in the past. This is the information in the future, and the knowledge of the past contains this amount of information about the future. It's this sort of, given by this overlap here. Okay, so I guess what this gives us then is a lower bound on how many bits any simulator or model of the process must store. Okay, that's how much we need to know about the past in order to be able to predict the future. Okay, but it turns out that if we go through the theory, the epsilon machine has to store more bits of information than are actually mathematically required in order to predict the future. So this excess information, E so-called, is less than this statistical complexity, C mu, that the epsilon machine has to store. And so this obviously then raises the question, are epsilon machines ideal, or can we find some way of storing information, less information, in a memory in order to sort of reduce this excess here between these two regions? Okay, to get rid of some of the recorded information that's not relevant for the future. So you're probably familiar already with this paper, which tells us that the answer to this question is that there is a way to reduce the amount of information that's stored, and that is by using quantum mechanics to reduce the complexity of classical models, of a classical epsilon machine. Okay, and without going into too much detail, the simple result is that there exists a quantum encoding, with some caveats, but we won't go into that now, such that if this epsilon machine complexity, statistical complexity, which I'm now using a sort of a lowercase c to mean classical, so my apologies for changing notation halfway through. If this is larger than the excess information, then there exists some quantum encoding with a statistical complexity which is less than the epsilon, classical epsilon machine's encoding. So from now on, I'm going to use this notation, c lowercase c for the classical statistical complexity, which I'll define in a moment, and CQ for the quantum statistical complexity. Okay, and so now we can come back to our random switch or coin model. And so now instead of just the possibility of classical states, zeros or ones, encoding the information, this one bit of information, we can say, well, maybe we can encode in a different way. We can use quantum states, and our causal states here will be this given by this ket 0 with the tilde on it, and the causal state corresponding to 1 will be this state here. Okay, so we still have two causal states, but they're encoded quantumly now rather than classically. And the idea then is to compare the statistical complexity of these two cases. So what we're doing is replacing bits with qubits, quantum bits. So our bits are 0 and 1, but really, of course, what we're thinking about is some sort of probability distribution over the bit. So in the model that we're talking about, in the equilibrium case, this is a 50-50 distribution over these two states. And we're thinking about replacing this with a quantum bit. Okay, so we can write our quantum bit, as you probably know, on a block sphere. And so as well as having these logical states, 0 and 1, we can also have any superposition of those, sort of most famously 0 plus 1 and 0 minus 1, and then the complex superpositions plus I1 and minus I1 as well. But in fact, we could have any superposition of 0 and 1. And so we live in this Hilbert space now, and we have a different system to think about. Okay, so let's go back to the classical case and just work through that for a moment. we've got two states. A zero state is one possibility, and the one state is the other possibility. Okay, they're the only two possibilities allowed classically. And as I said, on average, we're going to have, 50% of each. So in this diagram here, that sort of corresponds to some sort of, dot at the middle here, sort of an equal amount of this vector and an equal amount of that vector, just averages to this point in the middle. Okay, and when we come and stick those probabilities into the formula for the classical statistical complexity, then we find out that we get a classical statistical complexity of 1. Okay, so 1 bit there is the classical value for this epsilon machine. Okay, and so you probably saw, well, why would I draw the classical case on this kind of diagram, which looks a bit just like a plane of the block sphere that I showed before? And that's because we can actually, write our classical states as sort of a subset of the states allowed by the quantum system, by the qubit. And if we do that, then the only states allowed being 0 and 1, or some statistical combination of the two. This mixed state here in the middle, this sort of equal mixture of the two, this probabilistic distribution between them, corresponds to this mixed quantum state here. Okay, and what I want to do is compare that with what we get in the quantum case. Okay, so the idea of the quantum encoding is that one uses non-orthogonal representations, states that are not orthogonal on the block sphere. Okay, so I'll draw your attention to the difference between the 0 state and the 0 tilde state. These 0 and this 1 here at the top and the bottom represent our logical states, the sort of quantum equivalent of the classical basis, if you will. And these tildes are the causal states, and they're defined for the coin or the random switch model in this case. Okay, so P is the transition probability between the causal states, and so we can write down the 0 and 1 causal states in this way in terms of the logical states. Okay, and we can see that these are, for basically most values of P, these states are not orthogonal to each other. Okay, the average state then is sort of just given by the bisector that falls onto this line that joins the end of these vectors, in other words, this state here. And so the average quantum state looks like this, and you can see that it's not just the classical statistical mixture that we had before, but there's also some coherence associated with it as well. And so that tells us that the length of this vector isn't 0. We don't just have our average state here at the middle, but there's some length here which is somehow connected to the size of this transition probability. Okay, and so we can use the von Neumann entropy to tell us our classical quantum statistical complexity, just given by this expression here. And in the case I've drawn, where these two vectors are quite non-orthogonal, they're relatively close together, this value would be much less than unity. All right, so as P changes, the angle between these vectors will change, and the length of the average state will change, but nevertheless, as long as these are non-orthogonal, it's less than 1. When the states become almost orthogonal, it's still less than 1, but kind of close to 1, I guess. And then eventually we could have a particular case where P equals 0 or P equals 1. I've plotted the P equals 1 case here, where these states become orthogonal, and the quantum complexity and the classical complexity become the same, okay, because we have the same average state for the two cases. Okay, and so one can plot out what the statistical complexity in these cases look like as a value of, I think we should have a capital P here, the transition probability, and these are all sort of entropies here. And so we see that for the classical case, it doesn't matter for the value of P. It turns out that the average, you always have an equilibrium of equal amounts of 0 and 1, and so we always have 1 bit here. Except for this one exception here, this point at where the transition probability is equal to 1/2, then it's completely random, and we don't need to know anything about the state of the coin, and so one wouldn't really need to store any information. So at this sort of discontinuous point here, the entropy would be 0. But other than that, unity for the classical statistical complexity in all cases. And you can see that the quantum statistical complexity, as I pointed out, at the ends, at p equals 0 and p equals 1, corresponds with the classical case, and it dips down to a minimum in the middle. And so basically over most of this range then, the quantum outperforms the classical. A quirk, which we might want to talk about later on, is the idea that this mutual information limit is still lower than you expect for the quantum statistical complexity, and that's an interesting sort of discrepancy in this problem. Okay, so this is the idea of the kind of model we can have. We can have a classical model or we can have a quantum model, and we've seen why one might be interested in a quantum model because you store less information. What we now want to do is go to the lab and actually build what I'm going to call a simulator, which is a device which implements the model in a physical system in some particular hardware. Okay, and so obviously then the idea is that the results of the simulator should be equivalent to the system and to the mathematical model. In some sense, these things should be equivalent to one another. Okay, so to go from our model to our simulator, I'm going to use these circuit diagrams basically to describe what we did in the classical case, and in a moment I'll show you the quantum case as well. So basically what we're looking at here is one time step, okay? And on the top rail, so this is a conceptual diagram, and this is what we actually did in the lab. Let's talk about the conceptual one first. We've got the causal state here of the system. So in this case, the classical causal state, I've written it as a quantum ket, because as I said, we're going to encode our classical states into a qubit so that we can directly compare the classical and quantum case. It will undergo a flip with probability p, and then it will go on to the next time step. In order to read out the value of the bit at this time, we're going to do an XOR gate or a controlled NOT gate here between our system and or the memory state of the system, if you like, and some ancilla bit here. And so we just read this value onto the ancilla bit, and we can get out the value of the output of the model at this particular step. And then we introduce a new ancilla, and we repeat for each case. In the lab, we do exactly the same thing, except that we want to characterize the state of the system after each time step. And so we interrupt this, and we have this T here, which stands for tomography, which is the way that we characterize our states in the lab. And so we're interrupting the process, and then in order to do another step, what we need to do is sort of re-prepare the state that we would have had here, which we can do using this classical information and gate, and off we go. So this isn't really necessary in practice in the lab, but we just do it because it's a nice way of characterizing at each step, and also fits in well with the kind of hardware that we have operating. So the quantum case looks very similar. There's this sort of strange sort of crossover and inverting things here, but that's just because we're, for convenience, we're reading out the other quantum bit, the meter, instead of reading out the signal instead of reading out the meter. But nevertheless, the quantum causal state goes on to the next step, and we reintroduce our ancilla or our meter, and off we go. So this is really very similar to this in practice, except now these sort of double lines instead of these dashed lines mean that we're thinking about a qubit or a quantum circuit model rather than just looking at the classical case. And similarly in the lab, we do the same kind of thing. Again, we interrupt here so that we can characterize the state before going on to the next step. All right, so overall then, starting from the beginning and going right through, we had this sort of two-switch model, which we saw that was a naive model. One could represent it just by a single bit, by a perturbed coin. We can have a classical model for this with some transition probability between states at different time steps, or we can have a quantum model with these sort of shaded superposition states here that are not orthogonal, and we can have sort of conceptual and practical circuits for realizing both the classical and quantum cases in the lab. All right, so in the lab, what do we actually do? We need to, the main thing is implementing the controlled NOT gate or that controlled X gate, which allows us to map the information onto the readout. And so the way we store information is we use single photons and we encode in the polarization state of those single photons. Okay, so whether the photon is polarized horizontally or vertically. Of course, to make a quantum superposition, we need to be able to change the polarization state, which we can do with a series of wave plates. This is a general transformation. In the experiment we're doing, it's even simpler than that. Of course, at the end, we need to be able to read out the state of our system, and we can measure in any basis for the qubit simply with some wave plates, a polarizing beam splitter, and then some avalanche photodiodes, which allow us to count single photons. And in particular, one of the things that we want to do to characterize the average state, the average quantum state of our system, or the average classical state for that matter, is to do something called quantum state tomography, which is essentially repeating the experiment over and over and projecting onto different sets of bases, and then using these information about these projections to reconstruct the density matrix of the quantum state, or perhaps the classical state if we're just limiting ourselves to logical values. Okay, so the quantum operation itself we do with a linear optics or non-deterministic controlled NOT gate. So measurement provides the nonlinearity in the same way as the Canil, Laflamme and Milburn technique. And the key step, I won't take you through all the technical details, but the key step is if we have this 1/3 beam splitter here and a pair of photons meeting on it, then conditional on one photon coming out this port and one photon coming out this port, this sort of 1-1 state, one photon in each, is transformed to 1-1 state again. There's a non-unit amplitude here, which talks about the non-determinism of the gate, but most importantly, there's a minus sign here, a phase flip, a nonlinear phase flip, which gives us the nonlinear or quantum operation of the gate. In fact, this particular gate, as I've described it, is a controlled Z gate, so it rotates about the Z-axis of the sphere, not the X-axis, but one can simply just change the basis without too much trouble just by using some wave plates, and we can recover the C0. This is what it looks like in the lab. A laser shining onto a spontaneous parametric down conversion crystal generates a pair of photons. One of them we will encode our signal, or the memory of the simulator, onto using a wave plate to prepare basically either the classical or the quantum causal states here, okay, at each time step. And then we have a meta photon, as it were, our ancilla photon. Again, we can use a wave plate. That's what these yellow disks are, to prepare either just the logical zero case in the classical state or the zero quantum causal state here. Okay, this dash box here is the C0 gate. This is the non-classical interference I just mentioned before. And then at the end, these combinations of elements are the readout measurement that I talked about, and the avalanche photodiodes at the end. Okay, and so we use this measure and re-prepare scheme that I spoke about before to repeat this over and over, sort of from start to finish, as you were, and to look at the average states. Okay, so we did compute what the average states were, and obviously then calculated the classical and quantum statistical complexity from those. And as predicted, we can see that the classical, so we did this for sort of values of p between 0 and 1 in 0.1 steps. And we can see that the classical statistical complexity lies very close to 1, as predicted. At p is equal to 1/2, we actually still get 1, which is strange because we should get 0 down here. But this is because we did actually encode the bit in memory, even though it wasn't really necessary. So if you do encode the bit, you'll still have the same average state and you'll measure 1/2, but one doesn't need to do that in principle. The blue dots with the black error bars give us the statistical complexity for the quantum case, and you can see that up to some experimental errors, it follows the theoretically predicted curve reasonably well. And certainly these values lie well below the classical value. We generalized the problem a little bit more by saying, well, what happens if you have different transition probabilities between the forward and backward directions, p right or p left, if you will, and one can then write down different quantum causal states. These are still non-orthogonal, but they're not necessarily symmetrically distributed as about the horizontal axis as they were before. Okay, and in particular, we looked at this case where one of the probabilities is 0.3 and the other is 0.9. So we calculated the density matrices in both the classical and quantum cases. We're just looking at the real parts here. The imaginary parts are very close to 0. So this is the theory column, this is experiment, the classical row and the quantum row. And you can sort of see by eye that these things match up pretty well. And indeed, now we see a case where the equilibrium distribution in the classical case is no longer 50-50 between the logical 0 and the logical 1 state. And so the statistical complexity, even for the classical case, is reduced from 1. Okay, but the quantum statistical complexity is still significantly lower in this case. All right, so I'll just talk briefly about the next experiment that we've done, which Farzad will talk about more. So I'll just mention it in passing. It's the idea of taking this just a little step further and looking at modelling not just a single bit, but now a sort of a 1D chain, the 1D Ising model of spins. Okay, and so this is work that we finished in the lab, but the paper is in preparation. Okay, so the idea is that I think you're probably all familiar with the 1D Ising model. It's this chain of spins. There's some coupling between them, some external magnetic field, and we imagine that this thing is, in contact with an environment, and the environment has some temperature. And again, I apologize for the quirk of notation, but we're using capital gamma in this work to denote the temperature. So it's a strange choice, but we probably change that for the paper, but that's what we're using at the moment. Anyway, so the idea is that what we have now is this chain of spins, and it's a chain not in time like we had before, but it's a chain in space, okay? So we basically, each of these random variables now corresponds to a different physical location along the chain. But it turns out that one can in fact have a one-to-one mapping between the previous problem and this problem. And it turns out that if we sort of consider the half-infinite chain, I'm not going to go through details, but one can write down that there are in fact only two causal states for this problem. Okay, so it starts to look a lot like the problem that we had previously. There are two causal states, and there might be some different transition probabilities between those causal states, and those transition probabilities are related to the physical parameters that are of interest in the problem. So the coupling strength, the magnetic field, and the temperature. Okay, and so again, the classical models, the causal states are just bits, a 0 or a 1, a bit, and the quantum model has got this similar sorts of causal states to what we saw previously. So Jim flashed up a slide like this in his talk, where basically there's, again, a difference between what one expects to see in the statistical complexity classically and quantumly, and in particular there's this sort of turnover here in the quantum statistical complexity, okay? And this graph is plotted for a particular choice of magnetic field relative to the coupling strength, and in the ferromagnetic regime for the Ising spin. The experiment looks similar to before. There are some differences, which I won't say too much about because Farzad's about to tell you about it. You'll see that the gates are now a little bit more complicated, for example, and the procedure that we use to do the experiment is also somewhat more sophisticated. In particular, one of the things that we implemented here was the full characterization of the map that our quantum circuit actually does in the lab. Because one of the things about actually going to the lab and running a simulator is that these are not error-corrected simulators. These are things where the process that you actually implement in the lab may not be exactly the model that you set out to implement because of experimental errors. Okay? And so one of the things we did here was fully characterize our quantum circuit and then go back and ask the question, if our quantum circuit isn't perfect, if it doesn't perfectly implement the model or the particular set of parameters that we think that we're modeling, well, can we ask ourselves what is the closest set of parameters that our circuit does actually model? So we're actually trying to say, let's not pretend that our simulator perfectly implements the model. Let's ask what model does our simulator actually implement and really, be rigorous about looking at that and comparing apples with apples, as it were. Okay, so then we went on and we also, as well as just looking at average states of the system to calculate the statistical complexity, we also calculated statistical complexity from the final statistics as well. Okay, so we calculated the statistical complexity 2 different ways, which Farzad will tell you about as well. Okay, so I won't steal too much of his thunder. I'll show you one set of results, which is a different set. This is antiferromagnetic case. So in this case, the statistical complexities of the classical and quantum case are look a bit different from what we saw previously. But what we can see is that, whether we calculate the quantum complexity of the input at each time step, or the quantum complexity calculated from the output. By quantum complexity, I mean quantum statistical complexity. We can see that they agree pretty well with each other, and that they're sort of comparable to the theory for the particular sets of parameters that we modeled there. Okay, so I guess I'll wrap it up and leave a bit of time for questions. What we've looked at is we've been encoding memory for stochastic simulations in both classical and quantum systems, and comparing the statistical complexity in each case using photonic quantum logic, and we observed that the quantum statistical complexity is indeed lower, as predicted by theory. Some of the future directions that we're interested in are encoding more than 2 causal states in a qubit. So one of the objections that you might have to what we've done is that, okay, well, Geoff, the quantum statistical complexity you've observed for these non-orthogonal states is less than 1 bit, but nevertheless you still have a qubit to encode these states in. Okay, can we get an advantage, an actual resource advantage, by having 1 qubit compared with, say, 2 bits? So the actual physical number of systems you need to use is lower. And it turns out, in collaboration with Jane and Miller, we've got a plan for addressing that problem, and so encoding more than 2 causal states in a qubit and demonstrating that effect. In collaboration with Carlo and Miller and others, we're interested in chaining together in less of an interrupted way multiple sequential simulation steps, so that this is another stepping stone to doing more complicated things. We're talking with Jane about modeling input-output processes. We have a few other ideas as well. And then I've got my sort of ... question mark here. And I guess this is an opportunity for you to talk to us about the sorts of things that you'd be interested in us modeling, and we can have a discussion about what we're able to do with our system, and how we can sort of map your problem, your theory of interest, onto our experimental system as well. So with that, I'll conclude, and thank you very much.